10 fifth power dx. Would you like to do this one? I mean, this is 0 power tangent and then r power secant, right? Correct? So if you think along that line, this should be a hard problem, which we haven't talked about, right? But this is a special case where the power tangent, back case is even. It's actually 0, so it's pure power of secant, and it's a fifth power of secant. So what are you going to do with this? This one, so these two are typical examples. Here is how do you reduce the power of tangent, right? By isolating out two powers. So this is tangent squared x. Isolate two powers of tangent and then write it as secant squared minus 1. So that you have two terms in u equal. One of them, because of secant squared, you can use substitution. U equal to tangent, so that part is easy. The other part is similar to the original one, except that the power down by 2.
So would it be tangent squared plus 1?
Say it again?
Tangent squared.
Oh, tangent squared plus 1 wouldn't help. Because I like secant squared, because secant squared, is a derivative of tangent, so that I can use substitution, right? But tangent squared is not a derivative of secant, so it wouldn't help.
Oh, I was
right?
thinking along the Pythagorean identity, is secant squared.
Yeah, I know, right, yes. I would use Pythagorean, if I mimic that, then I would get, replacing secant squared by, as you suggest, the tangent squared plus 1. But I'm just saying that tangent squared is not as useful as secant squared.
What about if u equals to secant and du is secant tangent?
Say it again?
U equals to secant and, and du equals to secant tangent?
But then you have tangent, which we don't have, right? So here is that is a reduction formula technique, right? And here you have another reduction formula technique. It's one of those problems we talked about before, Jordan.
Okay, I'm thinking do a substitution. U is equal to secant 4 to the 4th power x, and then you have du as secant x tangent x du.
That will be secant 3rd power x and then secant x tangent x dx. That will be fairly complicated, right? Right, because if you let u equal to 4th power secant, then you du it, you have to take derivative of this guy, and that already have a power rule, along with chain rule, and the chain rule will give you secant tangent. So it'll be fairly complicated, right? Now, do you remember how we did this one? Reduction formula, Integration by part, does that ring a bell? This is secant 3rd power. This is secant 3rd power times secant squared power. But I'm not going to replace secant squared by 1 plus tangent squared plus 1. I'm not going to do that because tangent squared is not so useful, right? Instead, secant squared is far more useful, so I'm going to utilize that. So I'm going to use integration by part technique, right? So which one goes up? Which one goes down? Or what is u and what is dv? What is u? What is dv?
You want secant squared to go up.
You want secant squared. You want dv to be secant squared x dx, correct?
Yeah.
Yeah, so that v is tangent x, right? And that will means that if you have this, and then the other part will be what? Secant 3rd power x, right? So that's how you think of this as secant 3rd power secant squared, and then dx. So we have dx. So that dx along with secant squared x, does that give you du? Sorry, that du dv, right? And therefore v is tangent x. Anyway, if you use my up and down kind of version, then this one, I have two parts. I decide to, this secant square, I raise it up first because it's the derivative of tangent, so antiderivative tangent x, correct? Let me make it bigger. Secant third power x tangent x, right? Then minus what? Now this time you're going to, this one results from raising that secant square, right? And now you're going to copy over, so you have a tangent already, right? And then this one you're going to take derivative, what does that give you? 3 secant square x times secant x tangent x. That's the end of derivative, right? But then the other guy you copy over. The other guy is what? Tangent x dx, correct? So what do we get? Well, let's see. Let me rewrite it. Secant, that means secant x third power tangent x, secant third power x tangent x minus what I get is mu integral. First of all, it has a 3 here, correct? You have 3 here. Secondly, you have secant how many power? Third power. And then what? Tangent square x. That looks just as complicated as that one, right? Okay, but, I mean, I'm just using a specific example to remind you the general reduction formula. I mean, the way I derive this, the way I do here is just a special case of that general, reduction formula that you worked on before, where the power remains a symbol, n, right? But here is a specific case, right? At fifth power. So, I mean, this makes me sick. I don't know what to do because my nice older free one, I can't get the ink. And then I have all this kind, I don't know. This one is scented. So that makes it even worse, I think. It's an extra chemical, I think.
I have one if you need.
That's okay. Thank you. I think I'm trying to get some. I mean, the problem is that those odor free one, like this same brand Expo, they have odor free one, and those odor free ones dry up so fast. So we have got to replace the marker like crazy. Whereas the one that I usually use, actually at least I can refill it. But now I can't get the ink because they run out of stock, and for months I can't get it. So I don't know what to do. Okay, so
tolerance to the smell. So we bring the 3 out.
Okay, so yeah, that would be fine. But the key here is that somehow it is at this juncture I'm going to use Pythagorean identity. So tangent is what? Secant square x minus 1 dx. So this integral actually have 2 parts, two integrals. And one of them actually is what? 3 secant fifth power. And that is what, other than that coefficient is exactly what I'm trying to get. So I'm circling, but not that bad because it's of different coefficients, so I actually can solve it. Remember that? This is the game that we played last week. Right? So, assess the situation. This is secant third power x tangent x. And then I have minus 3 times what I want to find. Remember? What power? Fifth power? Mm-hmm. Exactly what I want to find. And then plus what? Plus 3 times secant lower power. Power 3. Power 3. Then from here, I know that at this moment, assess the situation. I want fifth power integral, and it turns out it is equal to secant third power x tangent x minus 3 times what I want, secant fifth power x dx, plus 3 times something simpler, lower power, third power, 2 power down. So that if I were to solve for this one, and let me show you, in practice, if you want to do it by hand, how do you manage your thought? Okay. You have this one step at a time computation, right? You start with this one, and this is equal to this. This is equal to that. It's equal to this. Is equal to this, which I copied, right? So I'll continue. Is equal to this, right? And then at that moment, you say that, okay, now I pause for a moment, and I see in my mind I have this equal to blah 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 minus 3 times this plus something else. And so now I can solve for what? This one. Then can you imagine how you solve it? Would you bring this one to the left? And that will become 4 times what I want, right? Is equal to something something. And then what would you do? Divide through by how much? 4. And therefore, the one you found therefore is 1/4 secant third power x tangent x. Correct? Right? And then what? Plus 3, also divide by 4, secant third power x dx. And that is the secant fifth power dx. So I managed to reduce this to something which is lower power. Then I have to do it again. Right? So how do I do it again? Now you deal with the next order of business. How do I deal with secant third power x dx? And then you repeat the whole process. Right? What did I do first? I isolated out secant squared. Secant squared is good, right? So I isolated it out. So I have secant x, and then you isolate out secant square x dx. And then what did I do? Then I do integration by part, right? So this becomes what? Secant x, and then what? Tangent x, right? So you raise this one up, and minus, you bring this one down. What is that? Secant x, tangent x. That's the derivative of secant. And then copy over tangent. Very complicated, of course, right? Then what do you get? You get secant x, tangent x, and then minus secant x, tangent square. What is tangent square? Secant square minus 1. That is the step, right? After the integration by parts, you have tangent square and replaced by secant square minus 1. And then you see that this is secant x tangent x minus what you want, which currently is secant third power x that I'm searching, plus secant x dx. 2 power down. Right? Okay? And now, so that means that, let me copy over secant third power x, which I'm currently looking for, is equal to secant x tangent x minus what I'm looking for currently, plus something simpler. And so once again, I solve for what I'm looking for currently. So can you do that mentally? This one move to the left. That's 2 times what I want. Then I divide through by 2. Same kind again. So what I want therefore is 1/2 secant x tangent x plus what? Plus 1/2 the simpler integral, which is secant x dx. Right? But do you remember what that divine inspiration? You know what I'm talking about? Secant x, what is out there doing it? Divine inspiration, that's a natural logarithm of, that's you know? Alright, so this is what? 1